Okay, finally, before we head into Chapter 11, I wanted to say one more thing about graphing categorical information or looking at line graphs. I'm going to show you some line graphs now. And here we're going to really focus on the axes. So again, our vertical axis, our vertical axis is the y-axis, and our horizontal axis is the x-axis. And here we're looking at, some surveys were done of college students, and we were looking at how much money the college students spent on textbooks. So on average, how much were they spending on textbooks? Now look carefully here at this graph, at this line graph, and we can see obviously the pattern is there's an upward trend. So as the years are going by, students seem to be spending more and more. Hopefully it's pretty obvious to everyone that there's this steep upward trend. Now again, look carefully at the y-axis here. You'll notice that here we have 140, 160, so it doesn't actually start at 0. It starts maybe around, I don't know, 120 or so. So that's something really to pay attention to. Looking at along the y-axis, looking at the increments or the intervals here, looking at where things are starting, how big the intervals are. Let's display this data in a slightly different way. So again, we have the same information. Year of the survey is on the x-axis, average spent is on y. Now we sort of expand our y-axis. We start way down here. So then we can still see there's an upward trend here, but obviously it doesn't look as steep as it did in this earlier example where the y-axis was more truncated. Okay, so expanding the axis can really change what is being displayed, can change the perception of the overall trend. What would happen if we shrunk the x-axis? So maybe we want to make it seem like there's an even bigger increase or a steeper increase than what we saw in that very first graph. Well, just shrinking the x-axis can make it seem like there's an even bigger increase. Here we're really shrinking the y-axis here. We're expanding the x-axis, and now it really seems almost like there's really no change, that it's pretty similar from year to year in terms of how much students are spending. So hopefully you're getting the picture here. Minor changes that you can make to your x and y axes can really change what your readers are perceiving, can really change the message that you're trying to convey. So that's something to think about. That's something to look for when you're looking at graphs. Does it look like maybe the person who put the graph together is just taking things out of context, that they're maybe compressing one of the axes to make the trend look different than it really is? So those are things to really look for carefully when you're reading different graphical displays. So always look carefully at the scales on the x-axes. You want to, or on the axes, not just the x-axis, but on both axes. You want to make sure things are labeled so you know what's being displayed. You want to make sure the intervals are even so that, again, the right message is being conveyed. Okay. So now we're going to move into graphing quantitative data, graphing amounts of things. And that's what Chapter 11 starts to get into. So Chapter 11 covers something called a histogram, which is a common way to graph quantitative data. There's also something called a box plot, which we're going to talk about when we get into Chapter 12. That's another way to graph quantitative data. Just quickly, a histogram will give you the full distribution. It'll show you all the different values and the remember, a distribution will show you the values that a variable takes and how often it takes those values, whereas a box plot is really just a quick summary of the data, so it's not showing you the full distribution. So let me show you a graph of quantitative data. So the graph below displays the number of years played in the Major League by 155 batters at the time they were inducted into the Baseball Hall of Fame. And so as you're looking at this, I just want you to maybe tell me what you think you can say about this distribution. If you had to describe this distribution, what are some things that you might say? So you might comment on where you think the middle of the distribution is. Like you might say, well, it looks like, you know, maybe around, I don't know, between 15 and 20 years on average is what the players were playing, or how many years they were playing in the major leagues. Or maybe you think the average is a little bit out this way. You know, where do you think the center is? You know, what would be a good measure of the center? Would it be the middle value? Would it be the average? When we get into chapter 12, we'll actually talk about different types of, or different ways that you can measure center. You might look at the overall range. You might say, wow, there were some players that, you know, obviously hadn't been in the major leagues for very long at all when they were inducted into the Baseball Hall of Fame, maybe not even a year. And there were some that were in there, you know, more than 25 years. So you could talk about the overall range. You might look at the shape. So you might notice that if you kind of imagine a smooth curve over this histogram, that the tail is pointing out toward the lower values. And so that type of shape has a particular name, and we'll learn about that shortly. So when looking at a histogram, you can focus on the center of that distribution. You can think about the variability of the distribution, the overall range of values, or other measures of variability. You can think about the general shape of the distribution. So one thing we really want to make sure everyone understands, and hopefully it's pretty clear from what you're seeing in the book and what I'll go through in this video, is just understanding how a histogram is constructed, what the parts are of a histogram, understanding what's on the x-axis and what's on the y-axis. So the x-axis, again, that's our horizontal axis. The y-axis is our vertical axis. The x-axis will always display the units of what you are measuring. So here we're looking at the heights of black cherry trees. So height is what we're interested in displaying. Height is what is on the x-axis. So always, always, always in a histogram, what you are measuring goes along the x-axis. And then the frequency is along the y-axis. And by frequency, we mean the number of individuals that fall within each of these intervals, or the percentage of individuals who fall within each of those intervals. So we want to be able to look at our x-axis, and we want to be able to know, okay, well, how many trees are between 60 and 65 feet? Well, the height of this bar will tell us the frequency. So 3 trees are going to be between 60 and 65 inches. 10 trees up here are going to be between 60 and 65 feet, not inches. 10 trees are going to be between 75 and 80 feet. Okay, so again, the heights of the bars will tell you frequency, or the number or percentage of individuals that fall within each of those intervals. Along the x-axis, that will tell us the intervals, that will tell us exactly what it is we're measuring. And a couple things to keep in mind. So we want to make sure, again, that these intervals are equal in terms of width. We want to make sure that the bars are the same in terms of their width. We don't want, you know, one bar to be much wider than another, because we know that that would be an issue with the area principle. Also, note here the y-axis, we call it frequency, but it can have other names. Sometimes you'll see it labeled as count, sometimes it'll be percent, so we might actually be displaying the number that fall within a certain interval, or again, the percentage. So we want you to understand that the y-axis can be labeled a little bit differently depending on who has created the histogram, but that value is always in reference to number or percentage that are falling within a certain category, or within a certain interval of our quantitative variable. So how are these graphs different? So I want to show you some histograms here, and I just want you to tell me what you think is different, other than the fact that they're each graphing something different. So the first one is the difference between the winning and losing point totals in all Super Bowl games. The next one is the weights in grams of a large sample of green M&Ms. And the last one is the years played in Major League by Baseball Hall of Fame inductees. Okay, so are you noticing differences? I'm hoping again that something that's really popping out at you is that each of these graphs has a rather different shape, has a distinctly different shape. So the first one has a tail that's pointing out toward the larger values, so it has most of its values are on the smaller side in terms of what's being measured, and then we have this tail trailing off to the larger values. The second one has more of a kind of a bell shape, where most of the values are in the middle, and then you have sort of an even number or a similar number on each side of the middle. And then the last one is one where the tail is pointing off toward the lower values. And so you have many values on the higher side and the tail is pointing off toward the lower values. So we call these distributions, or we have particular names that kind of describe these different shapes. So a distribution is skewed to the right or right skewed when the long tail points to the right. Again, if you imagine a curve over the distribution, the long tail is pointing to the right as you're looking at that distribution. If the long tail is pointing to the left as you were looking, then it's left skewed. And it's symmetric if you can imagine cutting the distribution in half and each side is a mirror image of the other side. So one type of symmetric distribution is a normal curve, as you see here, but you can have other types of symmetric distributions that are not necessarily normal. For instance, maybe you have something like this, where you have like a square shape. So we cut it in the middle, each side looks the same. Or maybe you have something like a U shape, like here. Again, we cut it in the middle, each side is a mirror image of the other side. So when you're judging skewness, again, you always want to think about where is the long tail. So that's how you judge skewness. You don't judge it based on where is most of the data. You base it on the direction that the tail points off to. If the tail is going to the right as you're looking at the distribution, it's skewed to the right. If it's going to the left as you're looking at the distribution, it's skewed to the left. Also, something to look at when you're judging shape is just how many peaks the distribution has. So the peak would be the highest point. So here, for instance, this is our highest point. There's one major peak. Here, again, we have kind of three bars that are sort of all together. So again, giving it one major peak right there in the middle. Here we have a peak. Here maybe, you know, we almost have another peak here, but we really have just, again, one major peak here. Sometimes you might have several peaks. You might have something that's we would call bimodal, like maybe you have a peak here and then you have a peak over here. So clearly that would be a distribution that has multiple peaks. A possible memory aid. So one thing that we've noticed is that sometimes it's hard to remember this idea of skewness. When you're trying to decide if something is right skewed or left skewed, you might get mixed up and you might think that skewness has to do not with where the tail is pointing off to, but where most of the data is. This is something that might help. So data that is skewed left has a tail pointing toward the lowest values, so the two L's here. This is, you know, sort of a mnemonic device that might help some of you remember this idea. I don't have a similar one for right skew, but if you remember left skew, then you'll know that right skew is just the opposite of that. Okay, so I think I'm going to stop here, and then we will come back and talk about some other things that you'll want to look at when you're attempting to make sense of a histogram, other than just focusing on the shape of the distribution.